So welcome back to our lecture, and let's quickly look again at what we just did before the break. We looked at the configuration where we had a fluid inside the reservoir at a stagnation state, and we let it accelerate in the open space in the limit of pressure in the outside going to zero. All the energy from the stagnation state is translated into kinetic energy. So obviously, we have exchanged energy, well, inner energy or enthalpy into kinetic energy. And this is an adiabatic process. So we did not add energy from the outside. There was no rocket engine, no combustion or anything, no propeller. We just exchanged, if like, potential energy or inner energy to kinetic energy. So this energy transfer is something quite interesting, and we can play with that. And let's look at this a bit more in detail. Let's do this on the other side of the blackboard. Let me write down again the energy conservation law. So what we just had before was Cp. Let's see here, Cp T naught. So the total energy in the stagnation state in the reservoir equals Cp T plus U squared divided by 2. Let's now modify this equation a little bit. First, we're going to divide it by Cp T naught. Obviously, on the left-hand side, we're just going to get 1. And then Cpt divided by Cp over T naught. And the second term will be U squared divided by 2 divided by Cp over T naught. Okay, so far, no magic. Now we're going to do something with these terms. Well, first of all, we're going to use the property that T is proportional to a squared. That's one of the basic relations for the speed of sound. So speed of sound is proportional to the square root of temperature, or temperature is proportional to the square of the speed of sound. So Cp T naught is proportional to the stagnation speed of sound, to A naught, and this is proportional to A squared. At the current state T. So this whole term here can just be written as A divided by A naught squared. Right? Because whatever the proportionality constant is, it cancels out in this ratio. Okay, so we have 1 equal to A squared over A naught squared. And what do we do with the second term? Well, on top, we have U half squared. Now, what is this here? Cp T naught. If we go back to the other side of our blackboard, actually, walk over, we see that Cp T naught is related to U max, or actually Cp T naught is just U max squared divided by 2. Okay, let's do this. Let's replace Cp T naught here by U max squared divided by 2. u max squared divided by 2. Okay, so we have rewritten now our law of energy conservation in this expression, and we can just kick out the 2 and let me put the flip it left and right. So we end up with this formulation. Plus u squared u max squared equals 1. So it's just an equivalent formulation of energy conservation. And let's see what it says, this formula, or how we can interpret that. If you think back of geometry, this is actually how we are defining an ellipsis, right? An ellipse, not a circle, but an ellipse, and these are the half axes. So this relation actually describes the geometrical figure of an ellipse, where we have one axis, the speed of sound, and one axis, the velocity u, and here we have a naught, and here we have u max, and let me see if I can do this. And this is, well, at least 1/4 of this ellipse. We have here the stagnation state. Where the velocity is 0 and the speed of sound is at a naught. And we can move along this line. Along this line, this equation is satisfied, and come to the point u max, where the speed of sound tended to 0, temperature tended to 0, pressure tended to 0. This is the extreme case. So we can move anywhere on an adiabatic system, we can move anywhere on this curve, exchange energy from the stagnation state into kinetic energy and vice versa. There's a line at 45 degrees exactly, where a naught, or excuse me, a and u are equal. So at this point, Mach is actually equal to 1. This is exactly the sonic state, where Mach is equal to 1. A has already decreased a bit, and u is equal to a. On this side, we're supersonic, and here we are subsonic. Okay? Next, as we go down here, we'd even come into the hypersonic configuration. So in practice, it's very difficult to even reach this u max. It's more of a theoretical situation. But along here, along this line, we can move forth and back as long as we conserve energy. If we put energy in the system from the outside, we're going to go to a larger ellipse. If we take away energy, maybe due to viscous dissipation, the energy ellipse becomes smaller. As long as the energy is conserved, as long as we're adiabatic, we're just moving on this energy ellipse. So this should give you a bit of an insight of how energy's enthalpy can be exchanged with kinetic energy. Good, so this is the concept of the energy ellipse. Let me show you the corresponding slide for that. Oops, sorry. Yeah, here you have the slide, essentially just said what I just did before. And now let's move to our main application for today's lecture, the flow in a nozzle. And to understand the flow in a nozzle, we again need to do some work on the blackboard. Again, we need to do some kind of manipulations like these. Let me use a different blackboard for that. The first thing we're going to do is to take the equation for conservation of momentum. So the Euler equation. The Euler equation, if you look it up, it says U du dx equals minus 1 over rho dp dx. This is what we had on the slide of conservation laws. It's part of Navier-Stokes. So let's manipulate that equation a bit. And first of all, we're going to multiply left and right hand side by dx, which essentially just cancels the dx's here, just to make it a bit more convenient. We don't need these dx's. The second thing we're going to do is we're going to expand it by d rho over d rho. Let's see what comes out of it. So on the left-hand side, we have u du, and the dx cancels out here. And actually, the d rho over d rho, we don't even write it, we just cancel it again. And so we just leave it like that. On the right-hand side, we actually got to use that d rho over d rho times dp. I explicitly wrote that out here. I'm going to rearrange these things a little bit. I'm going to arrange them in a way that we have minus. I put the d rho, take this d rho divided by rho, d rho over rho, and then after dp over d rho. dp over d rho. Just rearrange these terms a little bit. Now what do we have here? This is the total, or it's the derivative of dp divided by d rho. Under conditions that we were looking at, the flow isentropic, barotropic is actually a keyword here. We can say that this is just equal to the partial derivative dp d rho. So this is actually just equal to a squared. And this, if you look up on the slide on the speed of sound, this is how the speed of sound was defined, dp over d rho. So we have now u du equals minus d rho over rho times a squared. There's one more thing we're doing now, and we're multiplying this or dividing this equation by 1 over a squared. On the left-hand side, we have u times du over a squared. And if we actually expand this fraction by u, so we put a u here and a u squared here, then we get here u squared over a squared. So this is actually here just the Mach number squared, okay? And on the right-hand side, sorry, we have here minus sign, minus, the minus here goes away. We have a, just simply a d rho over rho. Okay, so finally we can write this as d rho over rho equals minus Mach squared du over u. So the final form. So it's just an alternative form of writing the momentum equation. And why have we done this? What have we gained? We have now learned that the momentum equation tells us something about the relation between the relative change of velocity to the relative change of density. And it's related via the Mach number. So if we have a 10% change in velocity, and let's say we have a Mach number of 1, exactly 1, then we have a minus 10% change in density. If we're in a subsonic configuration, this is smaller than 1, so a 10% increase in velocity leads to less than 10% decrease. If we're supersonic, a 10% increase leads to more than 10% decrease. Right? So that's what the Mach number is doing. It tells us how much density has to change in terms of the velocity change. And this now gives us a very good idea of how important this incompressibility effect is, or compressibility effect is. So this is telling us how much density is changing. And typically people are looking at the case where Mach is less than 0.3. At the Mach less than 0.3, Mach squared is less than 0.09. So that's less than 0.1. So that means a 10% velocity change times Mach squared leads to less than 1% density change. Okay? So there's one order of magnitude between velocity change and density change. This is why commonly people say if the Mach number is less than 0.3, the density changes are small. They're more than an order of magnitude smaller than the velocity changes. So for Mach less than 0.3, we can neglect compressible effects. This is really the rule that you use in practice. If you study a flow phenomenon, you look at the Mach number. If the Mach number is below 0.3, you forget about compressibility, you forget about today's lecture. If it's above 0.3, you better consider these effects. Okay, good. So this is just a side result because we can now do more with that. So we have now rewritten the momentum equation in this form. Now we can use the continuity equation or mass balance equation. Let me just write it down again. We had on a blackboard before the relative change of velocity plus the relative change in cross section plus the relative change in density must add up to 0. That's what this is telling us. And if we solve this for d rho over rho, so the relative change in density, it's equal to minus dA A minus du over u. Why did we do this? Well, because we can now take the d rho over rho that we had before on the other side of the blackboard on the equation for the equation for mass for balance conservation. Equation for momentum conservation here. Replace this over rho by what we have. Okay, so let's do this. So we obtain, let's say, with the Euler equation, this with the Euler equation then ends up being minus dA over A minus du over u. So this is over 0 over rho, and that is equal to minus Mach squared du over u. Okay, so this was our momentum balance before, and now we replace the d rho over rho by this expression coming from continuity. Now we can group the terms. We have here relative change of velocity. Here we have a relative change of velocity. We bring both of them to the same side, and we end up with the following expression. dA over A is equal to du over u times Mach squared minus 1. Or as it is more commonly written, it's du over u equals 1 over Mach squared minus 1 times dA over A. Okay, so we have derived now from continuity and from momentum balance an equation which relates changes in cross-section to changes in velocity. And there's a new factor in it. It's 1 over Mach squared minus 1. And we see that this factor here, this Mach squared minus 1, is negative for subsonic flows. So for subsonic flows, Mach squared is less than 1, minus 1, so this will be negative. So that means an increase in cross-section, there's a negative number, so an increase, minus sign gives a decrease in velocity, and vice versa. And I think this is intuitively clear. If we increase velocity, if we increase cross-section, we decrease velocity. If we decrease cross-section, velocity must increase. This is what we know from classical mass conservation. The weird thing is just happening for Mach larger than 1, for supersonic flows. For supersonic flows, we have the interesting situation that this becomes a positive constant, positive factor here, such that an increase in cross-section leads to an increase in velocity. So if we're diverging, if the nozzle is opening up, the velocity increases, and vice versa. If the cross-section is decreasing, if the cross-section is decreasing, the velocity is decreasing as well. So it's exactly the opposite from what we intuitively know. Making a pipe smaller will make the flow go faster. This is completely the opposite of what we know from incompressible flows. This has implications. Let me show you a few slides on that. So here we have this formula again, the one we just derived on a blackboard. And on the right, you have this schematic, which shows you 4 different situations. The top 2 are converging nozzles. Top left is converging, top right is diverging, and both for a subsonic flow. And there, everything is as we expected. A converging nozzle will lead to a decelerated flow, and the diverging nozzle will lead, sorry, I'm mixing it up. A converging nozzle in subsonic flow will lead to increasing velocity, and vice versa for a diverging nozzle. That's subsonic flow, very intuitive. The bottom row is the case for supersonic flows. There, a nozzle that is diverging will make the flow go faster. So if we have a supersonic flow and we're diverging, it will go even more supersonic than before. What about the case when the Mach number is exactly 1? Well, when the Mach number is exactly 1, look at the formula here on the left-hand side. Well, we get a 1 over 0, so that's not a very good thing. Well, maybe we put this term on the left-hand side, so we multiply by Mach squared minus 1. So we see that for Mach equals 1, the left-hand side is multiplied by the factor 0, such that the Mach equals 1 case is only possible if dA is 0. Okay, let me say this in clear words. The case Mach equal 1 is only possible if the cross-section is not changing, if we have a constant cross-section. If dA over A is 0, that's the only situation we can allow Mach equals 1. If we have a diverging or a converging nozzle, opening or closing, we cannot have the situation Mach equals 1. The only place where the flow can be exactly sonic is in the constant part of a pipe. These are very important results for what comes next. Let's look at the flow in a convergent nozzle coming from the left. And this picture you see on the right on top. We have flow coming from the left, let's say from a reservoir with a stagnation state. And on the right-hand side, we have a reduced pressure. And of course, this reduced pressure will accelerate the flow and it will flow into this nozzle. And let's say it flows into this nozzle coming out the reservoir. Well, first, obviously, will be subsonic because it starts at 0 velocity. And as the nozzle is closing, the flow will accelerate. That's exactly what we see on the diagram down here. This is actually showing the pressure. And if the pressure in this reservoir on the right-hand side is at the level A, the pressure will decrease. And as the pressure decreases, the flow accelerates as it goes through here, this throat of the nozzle. If we further lower the pressure to this point PB, there's a critical point PB, where the flow is getting faster and faster and faster, and it's coming closer and closer and closer to the Mach number, to Mach 1, to the sonic state. But we know that as long as the nozzle is converging, it cannot be exactly Mach equals 1. So the only state where Mach can be equal to 1 is exactly here at the throat of the nozzle. And this critical state, since we're subsonic, we can only accelerate and get as close as possible to Mach 1, and exactly here we reach Mach 1. Okay? In that situation, it doesn't matter if we further decrease the pressure on the downstream side. If we further decrease it, there will not be more flow going through this nozzle because this nozzle is limited by Mach equal 1. It will never get any faster than that. That is the situation of a choked flow. The nozzle is choked. What is happening upstream of this nozzle, or sorry, upstream of the throat of the nozzle, is then not affected anymore by this pressure. If it's below a certain level, it will just reach Mach 1 here, but it cannot go any faster. You can lower the pressure as much as you want, it will never get lower than that. So this is a choked nozzle. But let's continue this thought and let's ask ourselves, so what is happening if we add to the right of this design a nozzle that is slowly diverging? Because now we're here at the state with Mach 1, and if we're diverging, we can go into the supersonic state. And in supersonic, diverging means accelerating, okay? So there is a practical application to this nozzle, and it's a nozzle called Laval nozzle, which can be used to generate supersonic flows. You have here three designs, or well, three cases of this nozzle. Let's look at the left one first. We come in with subsonic flow on the left. The nozzle is converging, it's getting smaller. We're accelerating. We see here this in a Mach number, it's increasing, but we're always staying subsonic. It is at its highest point here in the throat, and because we stay subsonic, we're diverging again and reducing in velocity. Okay, so this is very similar to what we did in incompressible. On the opposite, we can start with supersonic flow and end with supersonic flow, and it's, well, the same, just the opposite, because the converging nozzle, the velocity is decreasing, but it's still supersonic at the throat, and we can go up on the other side again. The interesting case is this here, where we start with the subsonic flow, accelerate the flow, because the pressure on the right-hand side is really low. We accelerate it to the maximum possible velocity, which is at Mach 1, exactly Mach 1 at the throat. And on the other side, we're expanding it into a supersonic flow. This is how you practically generate supersonic flows by such a nozzle configuration. In incompressible flows, we call this a Venturi nozzle. We apply Bernoulli's law to sort of create vacuum or measure pressures. And here we're using the same geometrical design to generate supersonic. Let's look at a bit more systematically at what's really going on in such a Laval nozzle and play through a few cases. So we have the nozzle here on top of this image. On the left-hand side, we have a reservoir with a stagnation state P0, and everything is at rest. Pressure P is equal to P0. The Mach number is at 0 because we're at 0 velocity. And we're going into the nozzle in a subsonic state. Mach number is below 0. The nozzle is converging, and we're accelerating the flow. And let's look at the first case where we use, let's go here. On the right-hand side, the pressure that's just slightly below the stagnation pressure. Okay, so the flow is accelerated, the pressure goes down, reaches the maximum velocity here, but it remains subsonic and just goes back to slower velocity, following this curve here. So nothing really is happening. Maximum velocity is in the throat. As we lower the pressure from PA to PB, we're coming exactly at this critical state where we exactly reach this critical point where Mach 1 is reached. However, because the pressure is too low, we're just returning again at this bifurcation state to the subsonic condition. Only when we change the pressure and reduce it even further from PB to PC, let's see what is happening. At this point, we have reached Mach 1. And going back to subsonic is not an option for the flow because it would never reach the pressure C. It would not be a solution. So the only way for the flow is to become supersonic. Right here, supersonic. Except that if it was to follow this line all the way to the end, it would reach a pressure PE. But somehow the pressure at the end is PC. So there needs to be, and that's the only way, a discontinuity in the solution. There's a sudden jump from one state to another state, and that is called shock. And we're going to look into this in a few minutes. This is an actual shock where the flow goes from a supersonic to a subsonic state. Okay. Let's see what happens if we further decrease the pressure to PD. Well, if we go to further decrease pressure, the shock comes later and later and later until the shock is at the very end of the nozzle. But we still have a shock, but just at the end of the nozzle. PE is kind of an ideal singular case where the pressure is exactly that we have a perfectly expanded flow and there's no shock anymore and the flow can go out as a parallel supersonic flow. This is like a perfect generation of a supersonic flow. If we decrease even further, the flow has no possibility to sufficiently expand inside the nozzle and it will do something actually more complex shocks as it comes out of the nozzle. We're actually talking of an overexpanded flow if the pressure is here in this range between C and E, or between D and E. And we're talking about an overexpanded flow, an underexpanded flow with pressure. Please note that the flow in the nozzle looks the same as soon as we're beyond this pressure PB. The pressure, the flow condition here in the nozzle, in the throat, looks always the same. You cannot further accelerate it. The only thing that changes is the position of the shock, or if the shock is even outside of the nozzle. Okay, so here we have a choked nozzle, Mach equal 1. So what is happening in these shocks? So it's a strange thing, right? In fluid dynamics, everything is always nice and continuous, and only in these compressible flow configurations we can have flow discontinuity, which is called shock. Normal shocks, so a change from one state into the other, can be computed explicitly. There's one thing we need to relax, which we have not relaxed so far, and that is the isentropic condition. We need to allow for an entropy change as the flow is going through a shock. But because the equations are nonlinear, there's two solutions to it, and you can come up with so-called Rankine-Hugoniot equations, which you don't learn by heart, you just learn where to find them in the book. These are relations which relate conditions before and after the shock. There's this Mach number relation, and you see that the Mach number before the shock, which is always supersonic, relates according to this formula to the Mach number after the shock, which is typically subside. Instead of these rather intricate formulas, let us look at the diagram here. So this is just a visualization of these shock formulas, of these Rankine-Hugoniot formulas. And let's look at how we can read these diagrams. So let us assume we're coming with a flow out of our nozzle at the velocity of, at the speed of Mach 2. So we're on this line at Mach 2. And if we're going through a shock at this level, we end up here, we're crossing the line, the Mach 2 line, we end up with a flow on the other side of the shock with approximately, let's see how much this is, approximately, I would say 0.6. So from Mach 2, we're going to Mach 0.6. What is happening with the temperature? Well, the temperature increases, let's say, by a factor 1.5. After the shock, the temperature has increased. What is happening to the velocity? Well, the velocity will have decreased to about 0.4, the velocity after the shock. The density will have increased, and so will have the pressure. So these are the shock relations, and you need to tune the position of the shock. The position of the shock is always a variable thing. You need to tune the position of the shock such that condition before the shock and the condition after the shock, that they match the boundary conditions. So here, the position of the shock has to be tuned to the left and to the right such that the boundary conditions, and one is here the choked nozzle, and the other one here is the pressure at the outlet, such that they're being met. So it's a complex nonlinear problem to find the right shock position, but it can be done iteratively on a computer, for instance. So that's how you deal with these shock relations. Now let me come to the last 2 or 3 slides for today's lecture. Just to expand a little bit, we have now learned how an Lawson works, what a shock is. Now there are more complex shocks. So there are, for instance, oblique shocks. And this is now really going slightly away from our 1D case into a 2D case. So think, for instance, you have an airplane, a supersonic airplane with a fuselage. Fuselage would be down here, and you have a wing starting here. And here at this corner, you typically get a shock. And the question is, how can you compute these shocks? And it turns out that this whole oblique shock theory just works with 2 angles. One angle is this angle theta, that's the deflection angle. And you assume that the incoming velocity is parallel to the wall before the corner, and the outgoing velocity W2 is parallel to the deflected wall. And the second angle you have is the shock angle, which is unknown in the first place. And if you assume a shock angle beta as is here, you decompose the incoming velocity W1 into a parallel velocity V and a normal velocity U1. And on the outgoing side, the same. And you tune the shock angle such that the parallel velocities V are equal, because you say a velocity parallel to shock is not affected. And the velocities U1 and U2 satisfy the normal shock relations, the Rankine-Hugoniot relations. So it's a rather complicated thing, but technically it can be done. And again, there are diagrams for that, compressible flows, lifts of diagrams. And here's the diagram for that. So it shows here an object with deflection angle. Here it's called delta, and shock angle sigma. Let's assume we have an object with a deflection angle of 30 degrees. So if you have a deflection angle of 30 degrees, we are on this line here, 30 degrees. And if the incoming flow has a Mach number of 3, we can have an oblique shock either at an angle of approximately, let's say this about 52, 53 degrees, or we can have another shock. There's two solutions. We can have another shock of around 75 degrees. One is called a weak shock. This is the one on the left, solid lines, and a strong shock. This is the solution on the right-hand side. You see that in strong shocks, the Mach number becomes subsonic, whereas in weak shocks, the Mach number remains supersonic. And typically, you end up with a strong shock, so you end up with a lower subsonic Mach number. So most likely, you will end up with a shock at an angle of about, what is this, 74 degrees. Now let's assume this object is slowing down, and we're coming to a Mach number of only 2, and we have a reflection angle of 30. And you see that this line here, the curve for Mach number 2, never crosses at 30 degrees. So there is no oblique shock for a Mach number of 2. There's actually, as the Mach number decreases from 3, that's this line, to 2, there's like a critical Mach number where you have only one unique shock, and that's exactly here at this dotted line, which is about the 64 degrees, okay? So the Mach angle, the shock angle goes from about 72 to about 64. And if you further decelerate, there is no oblique shock anymore, and we obtain a so-called detached shock. So that is a phenomenon you have if you have very large deflection angles or too low velocities. And that's something you see, for instance, in a blunt-nosed object. So like the space shuttle, which has a blunt nose, it will have essentially deflection angle of 90 degrees because it's a blunt nose, and you always have detached shock in front of that. And there you go through strong shocks, weak shocks. This becomes very quickly very complicated if you go into that. But I just want to present you these phenomena in principle. Okay, so we're nearly done. Just one last phenomenon. In the oblique shock, we looked at what's happening if the wall is concave, if it's coming up. Question is, what is happening if we have a convex corner, so if the wall is going down? In that case, we don't have a shock anymore. We have a continuous solution, and the continuous solution is a so-called expansion fan. And again, the flow here, because we have a diverging case, actually, we are accelerating the flow, going to a higher Mach number, actually. And we have these expansion fan lines, which are defined by the so-called Mach angles. But I'm not going to go into any more detail on that. I just want to show it to you, to tell you there's more of these phenomena. So pretty much this closes today's lecture. I just want to end up with this picture with a few examples without discussing this in any detail. I just want to show you that compressible flows in the experiment up here. These are probably Schlieren visualizations, like showing density changes in the flow, showing like here a nice detached bow shock, or here very classical oblique shocks coming off a supersonic airplane, or here like a pointed, probably a missile or something like that. And down here in practice, complex shock cells, diamonds they're called because they have this diamond shape, which are very classical. They come out of jet engines at that supersonic speed. So it's a combination of shocks that are being reflected in a jet. And here, classical oblique shock, which is usually connected to a sonic boom when planes go supersonic. Okay, so I hope I have not confused you too much. It's a bit of a different story, compressible flows compared to incompressible flows. But it's a beautiful topic. It is, physics are more involved here. I would say it's more complicated. At the same time, it holds many beautiful phenomena that we don't see in incompressible flows. So with that, I would like to close here and say goodbye to you. Next week, we're going to meet again to talk about experimental methods. And I'm going to hand over to Kai for the exercise class and say